I wasn't completely happy with the original circuit that was using a high pass filter, so I thought I'd try a low pass filter instead. The problem with the high pass is there's an awful lot of harmonics coming through, higher frequency stuff coming through from the oscillator, and of course that goes straight through the high pass filter. So by switching to a low pass I can get rid of all of that and just focus on the two frequencies out of the oscillator. So this is the modified circuit. To convert the low pass in the high pass into a low pass, you basically just swap the two capacitor and resistors around, which I've done here. I've also tweaked the values. In the previous circuit I was using capacitors of a few nanofarads. That seemed to be having an effect on the oscillator and lowering its frequency. It still functioned, but I thought I would take them down an order of magnitude and increase the resistors accordingly. So the resistors are now 47k instead of 4k7, and on the breadboard I'm actually using 150 picofarad. For the sake of the SPICE model I've had to increase these to 250. The oscillator is essentially the same as it was before. Again, this has been modified in SPICE just to make sure that the output is consistent with what I'm actually getting. And if we run this and have a look at the output frequency, that's pretty close to what I'm getting from the op-amp itself. A quick Fourier analysis of that will show us the natural frequency, which is around about 15 kilohertz, which is what I'm getting. And if I drop down to my 47 picofarad or thereabouts, which is me not touching the sensor, then obviously the frequency increases somewhat. And when that completes, if we have a look at the frequency, we're getting around about 25 on the oscilloscope, and this is saying slightly over 25, so that's exactly matching what we were getting on the breadboard. The filter itself is giving a pretty reasonable output. If I disconnect this capacitor here and have a look at the output, we can see that we're getting a fairly solid 4-volt output with a bit of ripple. As we'll see in a minute when we look at this on the breadboard, this is pretty consistent with what we're actually getting, although I am using slightly lower value capacitors on the breadboard. I expect the breadboard capacitance is bumping that up a little bit. And then if we simulate what happens when I touch the circuit and run it again, we see that we're getting much lower spikes. The reason the output is high when there is a high frequency going in, which should be being filtered out, is because essentially this output is a 2 volt plus or minus around a 2 volt DC bias level. So if we're filtering all of that out, we shouldn't be expecting to get anything through here, although we will get a little bit. It will be attenuated. Drop that down to the 50. You can see that we're getting essentially around 2.1 volts. So that means that that's going into the non-inverting input because it's a non-inverting amplifier. So that means that the signal at the inverting input should be essentially the same, and of course it is, close enough, rippling around that. And because we've got a 50k and a 47k divider here, which is where we're taking our inverting input from, obviously the voltage here would have to be double whatever the voltage here is. So if we're getting about 1.8 volts there nominal, we should be getting a little over twice that, about 2.1 times that, which is why we're getting about 4 volts there. So basically when we've got a high frequency signal which is being filtered out, our output essentially goes high to 4 volts, and then when we increase our capacitance by touching it, if I pretend I'm putting 100 picofarads on and run it, you can see that we're now getting a frequency coming through quite clearly, a motorbike going past quite loudly. And obviously if we filter that and take the average, we're going to get a lower value instead of the 4 volts that we were getting. So that's the modifications that I've made to the circuit, and then it's going into a comparator. I've tweaked the resistor values just so that they work a little better. I think I'm using a 10k on the breadboard and some fairly robust filtering on the output. The reason for that is because if we look at the output, there we go, that's essentially our low output. When I'm touching the signal, we can invert that obviously if we just swap the pins over, and then when I'm not touching the sensor plate, you'll notice that we get a bit of a voltage spike just as we switch the circuit on, and then it settles down. This is actually why I was trying to use a high pass filter in the first place, because you don't get that little spike there. But by putting some fairly robust filtering on the output, we can mitigate it, and by feeding this into a second stage comparator with the threshold set somewhere above here, 2.5 volts say, that's not going to make it through at all. So that's the modifications to the circuit. The op amp is actually oscillating pretty close to its maximum. It can only slew its voltage up and down so quickly, and if you look on the data sheet, a 0 to 4 volt swing would take roughly around 15 microseconds. So going up and down 30 microseconds, take the inverse, that's about 30 kilohertz, and that's pretty much as fast as we can run this thing before we start getting some attenuation on the output. So anyway, there's the circuit. We'll now have a quick look at it on the breadboard, and then I'm going to build a proper circuit board for it, populate it, and see if the thing works in practice. This is the modified circuit on the breadboard. Not a great deal of changes from the original one in the first video. The yellow trace on the digital scope is our natural frequency of oscillation, which is saying 26 and a bit, 27 kilohertz. As you can see, it's ramping up and down in a triangular fashion. There's no square wave here, there's a little bit of squareness at the top, and if you look very carefully you can see that the up and the down are very slightly different. This is probably because the output stage for a 324 is I think it's a Darlington configuration, a Darlington follower on the high and a saturated NPN on the low side, so they're going to switch at slightly different speeds. The Darlington is probably the slower of the two, but it's a fairly convincing, not quite sinusoidal output, but close enough. And when I touch the plate, that drops to about 15 kilohertz. We can see far more clearly now how the downstroke is different from the upstroke, and we're also getting a bit more squareness at the top because we're running at a lower frequency. So that's about the maximum, maybe a little bit under the maximum of what the op amp can deliver in terms of that sort of voltage swing and that sort of frequency range, and there's our fairly clear signal. Now the blue trace is the output from the filter. As you can see, it's about, if I swap that to channel 2, it's about 3.5 volts average, and when I touch it, it drops to about 2.8 volts average. There's a bit of ripple in there still. I could put a slightly larger capacitor in there filtering it. I think it's a 4.7 microfarad filtering the output from the low pass filter. So that's working quite nicely. If I actually disconnect that filter capacitor and drop the time base a little bit, we can see that's the sort of output that we were seeing in the SPICE simulation, nominally at about 3 and a bit volts with a bit of ripple on it, and when you touch it, it drops down, and quite a lot of distinction between those two signals. So that's the low pass filter working fairly well. And if we reconnect that capacitor, that's in, and you can see that just takes the edge off all of that spikiness. And then on our analog scope at the bottom, this is our output from our comparator. If I'm very, very gentle on it, you can see there's a bit of flickering in there as it transitions. I think using the 4th op amp in this circuit, which is spare, I put that output into another comparator just to make that signal change a lot more robust. But that's working fairly well. I've tried it with a piece of paper over it and it still works, so you don't actually need to be touching the metal itself. It is quite sensitive and does the job, so I think a low pass filter is the way to go on this circuit. Next stage, let's build a proper circuit board, populate it and see what happens. Having got the circuit working successfully on the breadboard, next stage is to transfer it to a proper circuit board. Going to need some sort of voltage regulator because I don't know what voltage it's going to be running off, and the circuit's designed for 5 volts. Could use a 7805, but I tend to prefer using the 317s because it gives me that adjustability. I'll probably use something like a 220 and a 680 will probably give me 5 volts. I think this is pinch from another circuit. Going to end up looking something like that, I suspect. Might put a variable resistor on the output. Not essential, pretty standard stuff. Our oscillator stage will look a bit like this. Here's our 100k voltage divider onto the non-inverting input, which is giving us our reference voltage at about 2.5 volts, and then this 4k7, which is connected to the output, will modify that accordingly. If the output goes high, it'll pull this up beyond 2.5, and when the output goes low, it will pull it down below 2.5. Over here we've got our charging resistor. I was intending to use a variable resistor here, but I'll probably start by just trying the 22k that we used in the first place, and then here's our 47 picofarad capacitor in parallel with our touch plate. Low pass filter looks a bit simpler when drawn up like this. We've basically got two low pass filters here, resistor capacitor. Normally this would go to ground, but instead it comes to this voltage divider, the top of this voltage divider, and that feeds back into our inverting input, and our non-inverting input is down here. And then the final stage, the comparator. Going to use a variable trim pot here to set the threshold, some smoothing on our input, and I'll double it up so that we get rid of any extra ripple that might be coming through, and these values don't really matter too much. 100k and 100k will be fine. So converting all of that into a circuit board layout is going to look something like that for the oscillator, and something like that for our filter stage, and then something like that for our comparator. And I thought, just for the hell of it, I'll throw on an LED through a 470k resistor so we can see when the plate has been touched, and a 1k base resistor going into a quad 2 with an open collector, just in case we need to run something different from a 5 volt output. And then bringing all that together, we get a circuit board which is going to look something like this. Add a few test points on here so we can see what's going on. Nominal 12 volt input perhaps. I'm probably going to run it off a 9 volt battery, to be honest, and a 5 volt test point, or we can just feed 5 volts straight into there. This is our link which is going to go out to our capacitive touch sensor, basically a plate of metal of some description. And apart from that, it all looks pretty straightforward. So now I've just got to build it, test it, and hope it works. So this is the PCB that I've made. It's been cut out on the CNC rather than etched, so I'm just hoping I've got everything right, but there's only one way to find out. About halfway through populating the board, I've put a 317 regulator on here, and I'm getting, according to the scope, 5.26 volts out, which is a little higher than I was running it before, but it shouldn't be a problem. But most importantly, if I look over here, that's the frequency I'm getting out of the oscillator, which is 27.8 kilohertz, so a little bit higher than I was getting originally, averaging 2.3-ish RMS. So the breadboard capacitance wasn't actually making an enormous difference. I've gone with the 22k that I was using in the original circuit. I was planning on putting a trim pot in there, but I thought I'd just try the 22 to see what happened, and all is good so far. I haven't added the capacitive touch plate yet, so I can't show the frequency dropping, but I did test it a little while ago and it seemed okay. So next stage, put the filter in. And this is the circuit with the 2-pole Chebyshev filter in it. It's giving an output of around about, very ripply, not even quite picking it up on the scope, but that's pretty much what we were expecting. And when I touch the plate, it drops to 13.5 kilohertz, so that seems to be working quite well. I haven't added the output filter capacitor yet. I'll do that and tag on the comparator, and with a bit of luck the circuit should work. So this is the final circuit board, all populated. The only problem is it doesn't work. Discovered at the last minute that basically it needs a ground reference. So if I ground this to a mains earth, it works. If I ground it to even the power supply, which isn't switched on, this is battery power supply, so there's no mains earth here, but it still works. And if I'm touching it, it works. But without that reference, the circuit doesn't actually run. So it needs some sort of a secondary plate, if you like, for the capacitor, and it has to be connected to something, but where this is going to end up, it's probably going to be okay, because there'll be other things that we can connect it to. So that's a very simple and cheap, looks a little bit more complicated on the board than I anticipated, but that's a fairly simple and cheap capacitive touch sensor.